Hello everyone, and welcome. Today we are going to talk about a major breakthrough in AI agent design called ContextWeaver, which represents the architecture of deliberation. We'll explore how we can finally move large language model agents away from simple linear memory and upgrade them to use dependency-structured causal graphs. Let's dive in. To understand the problem, we have to look at the explosive growth of agent context. When LLM agents interact with tools, like running bash commands or searching the web, they generate a massive triad of data for every single step: thought, action, and observation, or TAO. As an agent goes about its task, this trajectory lengthens rapidly, and we quickly hit the model's token limits. This forces a very critical decision: when our memory gets full, what exactly do we discard? Right now, most systems fall into what we call the recency trap. Current context management relies on strict recency, typically using a sliding window that blindly drops older turns. The problem is, this physically severs the logical chain between an early discovery and a later implementation. The agent effectively suffers from induced amnesia, which breaks its ongoing plans and forces it to repeat explorations it already did. Let's look at the current agent memory landscape. If you use a sliding window, you're relying strictly on recency, which causes that amnesia. Semantic retrieval methods, like IMEMGPT, use vector similarity, but those can lead to hallucinations. Simple LLM summarization compresses text, but loses fidelity. ContextWeaver takes a completely different approach. It selects memory based on causal and logical flow, structuring it as a directed acyclic graph, or DAG. This approach provides validated execution feedback and is highly robust against failures. This brings us to a major paradigm shift. Instead of organizing memory as a flat, linear stream of text over time where a sliding window simply chops off the past, ContextWeaver transforms the entire interaction trace into a map of information flow. It weaves a context based strictly on the reasoning steps the agent actually relies on to get the job done, rather than just looking at what happened last. So, how does it work? The ContextWeaver pipeline operates incrementally and has four main steps. First, it converts raw text into a structured node. Second, it uses LLM analysis to link that node to its logical parents. Third, it traverses the graph backward to collect an ancestry subgraph. And finally, it weaves this final context together so it perfectly fits within our token budgets. Let's break down step 1. Every time the agent generates a thought, action, and observation, that raw text is distilled into a structured anatomy, a UI card of sorts. This card contains a node ID, a summary of what happened, a narrative of the reasoning path, its parent nodes, and a validation status to see if it actually passed or failed. In step 2, ContextWeaver completely abandons blind vector similarity. Instead, it uses an LLM as a logical dependency analyzer to evaluate physical dependencies. It literally asks, does this current operation need the specific result from that previous operation? It rejects nodes that just have similar keywords but no real information flow, and explicitly accepts nodes that have true causal and logical links. Once the parents are assigned, step 3 comes in, ancestry traversal using a breadth-first search. The agent searches upward through the graph to retrieve the exact subgraph of decisions that support its current goal. This is brilliant because all of those irrelevant parallel explorations and dead ends are gracefully left in the dark, preserving your valuable token budget. For step 4, we have observation compression. For any history entries that fall outside of that active, necessary subgraph, ContextWeaver retains the thought and action but dynamically compresses the really heavy observation payload. This means the token budget is secured by smart structural selection, not by aggressively summarizing everything until the meaning is lost. There's also a built-in validation layer that paves a reliable road for the agent. ContextWeaver actually parses the execution outcomes to assign validation labels. Any nodes marked as failed or superseded are simply skipped during the parent search. Because of this, new reasoning steps literally cannot attach to incomplete or broken states. When we synthesize all of this, we get the true architecture of deliberation. ContextWeaver is not merely a memory compression tool, it is a full self-correcting reasoning engine. The graph maps the territory, the summarizer compresses the path, and the validation layer paves the road. Together, they physically prevent an agent from building new actions on top of broken logic. And the empirical proof backs this up. When tested on the SWE bench results, ContextWeaver consistently outperformed the sliding window baseline. Whether it was Claude Sonnet 4, a GPT-5 hybrid setup, or Gemini 3 Flash, ContextWeaver improved the solve rates across both verified and light environments. The hybrid setting even proved that strong models benefit massively from this structural retrieval. What's really amazing is what we call the efficiency dual win. You might think better accuracy requires a bloated context window, but it's actually the opposite. ContextWeaver solves more problems while reducing the average tokens required per successful resolve, and it requires nearly 5% fewer iterations overall. By selecting context based on true dependencies, it entirely eliminates wasted cycles on irrelevant branches. You might be wondering, why use a directed acyclic graph instead of a simpler tree structure? The answer is structural stability. When researchers restricted the memory to a tree, it resulted in nearly double the run-to-run performance variance, a standard deviation of 2.92. A DAG, on the other hand, drops that variance to 1.55. By allowing multiple parents per node, the DAG synthesizes information across multiple previous steps, absorbing exploration shock and giving the agent a much more stable memory backbone. However, dependency-aware memory is not a silver bullet. You have to know when to deploy it. ContextWeaver thrives in tasks with high cross-component complexity and branching logic. But if your task is strictly localized and sequential, you are still better off relying on the lightweight sliding window zone. Let's look at a trace analysis to see this in action. In a complex multi-component task like Django 14631, the sliding window drops early architectural context, forcing the agent into an agonizing 83-step loop of amnesia where it just keeps rediscovering the same things. ContextWeaver, acting like a structural bridge, maintains those persistent links, allowing the agent to cleanly solve it in 71 steps by connecting cross-file relationships established 50 steps prior. But, in a localized, sequential fix like PyTest 7205, the sliding window is highly efficient, solving it in a clean, linear 27-step trajectory. Here, ContextWeaver actually introduces unnecessary branching overhead because it keeps trying to build distinct ancestral contexts, stretching the process out to 59 steps. It's a great reminder to pick the right tool for the job. Ultimately, ContextWeaver proves that organizing memory by logical flow improves reliability under fixed budgets. As we move toward the future of multi-agent systems, maintaining these explicit causal dependencies won't just be a nice feature, it will be absolutely essential for coordinating reasoning and preventing systemic amnesia across our AI systems. Thank you for watching. Would you like me to create an audio overview, podcast format, from these slides to further experiment with this topic?